So now let's go ahead to talk about the transistor. I'm going to review it, how it operates. I think all of you need to know how it operates as an electrical engineer. We already briefly say how it operates, right? So again, I have a source, I have a drain, and then I have a gate. So it's a 3-terminal device. But we only care about 2 terminals because our goal is to use the 3rd terminal to control the conductivity in the other terminal, right? So we have the gate metal here, or gate poly, and then here is the insulator. Here you always need to remember this is, I just call it SiO2, the insulator. Right? It's always insulating. And then what does it mean? It forms a capacitor. Right? Conductive metal on the top, and then substrate. If substrate is conductive, then that's just a capacitor. So that is the concept you need to have, right? You know that I am going to control it capacitively. Now let me assume that now the gate voltage is at 0 volts and the threshold voltage is 0.7. So at this point, Vg is smaller than Vth. Okay, so you are going to maybe it's easier, right, to even say that the Vg is negative if you don't feel comfortable out there. Otherwise, just agree that because it's less than Vth, much more less than Vth, you're going to attract the hole to the surface, right? And I forgot to say this is p-type, so I have a lot of hole here. Not p, I should say h. I have a lot of hole at the bottom, right? And I also attract some hole here. Correct? So from source to drain, what do I have? I actually have this. A back-to-back PN diode. This is source, this is drain, and this is the body. Because this is N, this is P, because I have lots of hole, and this is N. So, am I going to get any conduction? No, right? And I just say that we accumulate of a hole. This is called accumulation. Why I call it accumulation? Because the substrate started with p-type. I have a lot of hole. And now I apply a negative voltage at the gate. It attracts even more hole to the surface. We care about the surface. So it's accumulate. It accumulates a lot of holes. Okay, so then we decide to start increasing the gate voltage. Now this gate voltage is 0.5, which is still less than Vth. What will happen? When I start increasing the gate voltage, it becomes less attractive to the hole, right? Because increasing the gate voltage means the potential keep increasing. It's just like the, how to say, it was like a pond, right? A lower land, you keep attracting the water. Now I raise the level, then it will be less attractive to more water molecule to come in, right? I keep raising, right? So this hole is going to be repelled away, right? I have a lot of hole here, and now they got repelled. But do you remember how you get a p-type doping? You actually have some dopant, and this dopant will release the hole. For example, the boron, right? So you will leave some ionized atoms which is negative charge because you take away the hole, right? Now this is a little bit difficult to imagine, right? But let's think about the other type. Let's say I have an N-type. The N-type is what? I have the phosphorus, then I have an extra electron, right? And together with that electron, I'm neutral. Now if you take away my electron, I become positive. So similar, you can think of boron have an extra hole. I was neutral. But now you repel away my hole, I becomes negative. Because myself, the boron plus that hole is neutral. Is that okay? Yeah. But anyway, I repel the hole and then I leave some ionized atom behind. This is called, this mode is called depletion. Why? Because I depleted, the holes are depleted. I remove the hole. That's why it's called depletion regime. Right? So I start with accumulation, a lot of money, a lot of hole. And then now I push them away. I'm depleted of money, depleted of hole, like this. Okay? But if I keep increasing the gate voltage, now this is larger than VTH. Besides depleting the money, I'm attracting electron to myself, right? Because electron is negative charge, right? It's just like I deplete the money and then now I'm attracting a lot of debt, right? Opposite, right? Having debt and having money is opposite, right? So now I have some negative charge here, but they are free electron. Now, okay, I forgot to ask this. Here, can we have any current? I have negative N plus here electron. I have negative charge here, but ionized atom, which are fixed, immobile. And then I have negative electron again. Do we have any current? No, because even you are negative, you cannot flow. Current need to flow, right? Just like I have water on both sides of my tube, but at the center, it got frozen. They are ice. Do you have current? You don't have current, right? But now it is different. I keep increasing the voltage, so it is larger than the threshold voltage. Besides that, it have the ice, I also attract more water molecule, right? It's just like now I attract a lot of free electron. So you just become a pure resistor. Electron, electron, electron. Then you have the current, right? So I need to say this current equal to 0, this current equal to 0, and here now eventually have current larger than 0, right? Because now I have the free electron. Ah, thank you. Thank you. I know what you say. Okay. First, but I will fix it later. And now, this is called inversion, right? Why is called inversion? Because the body was p-type. Now it becomes n-type. That's why it's inverted. So inversion, right? So you don't need to know this detail, but I hope you can, you have the idea, just like I don't need to know how my car works, but I know very well how I press the brake, what I need to do when I turn left, turn right, all these signal lights. This is just an instinct because I live with that, right? As an electrical engineer, I hope you have this idea. Okay, I forgot all this potential, but remember, of course, I start with accumulation, not flowing, and then depletion, then inversion. And the reason is the accumulate of the charge that I don't want, and eventually inversion of the charge that I want. That's why it's flowing, right? Have this picture in your mind, right? So he has a good point saying that the current won't be 0 because I put zero potential at every place, right? So maybe let me just erase this, so you won't get confusion. But here you just say that we form the channel. If you apply the right potential, it will flow. Okay, good point, right? So let's review some concept. There is a maximum depletion width when we're depleting it, and then eventually we will accumulate the electron. And why is that? Because once you accumulate the electron, the inversion layer will screen the electric field from the gate. Okay, so we keep depleting, pushing the hole away, but eventually it is replenished with a lot of electron, then we are not going to deplete more. What is threshold voltage? I think you know that, right? After which it should be we should say the gate voltage, it is just the VG, after which the inversion layer is formed. Okay, so I hope you remember this. What is threshold voltage? Keep increasing VG. After that, the inversion layer is formed. That's why it is called threshold voltage. Okay, and another thing I want to reinforce is that why we have more mobile charge when the VG keep increasing. We already say that because of the electric field, right? But basically, this is just due to the capacitive coupling. This is just a very simple problem that we have a capacitor, Cox, there. I keep increasing the voltage on one side. Of course, I will keep increasing the positive charge another side, right? Because you will keep attracting more, negative charge, I'm sorry. Positive charge on one side, negative charge on another side, right? So the idea is that how I increase it? Because I have capacitive coupling, okay? So this is an overview. And this is just to re-illustrate that the concept, again, transistor is just a resistor, and then we couple through this capacitor. It's just now that this resistor is a function of gate voltage. It depends on the gate voltage. I already showed you it depends, right? Because it starts from infinite resistance to finite and even smaller when you increase the gate voltage, right? And this will be useful, for example, to use as a voltage control attenuator, right? You just use the potential divider equation, right? Then this is R1 divided by R1 plus Rm, which is a function of Vg times Vin, right? Just a simple concept. Now, so we know some hand waving idea of the transistor. Maybe we can try to guess what it looked like when we measure it. Now, I try to add a VG here. And then let's say we have a voltage of, let's say, 1 volt, for example. And I want to start increasing the VG, right? I want to increase the VG and see how the current goes. This is called IDVG, right? So let me repeat what I said earlier. When I have a let's say my VG is much, much smaller than VTH, it's going to attract what? Oh, thank you. So in this case, it is in the accumulation mode. Okay, so I want to plot it. I want to see what it looks like. I try to keep increasing VG, and I measure the ID. What do I get? Flat 9, okay? Zero current, because I equal to 0, okay? Now, and then I go to another regime. I make this maybe just equal to VTH. Right? I keep increasing. At this stage, do I have any electron just at VTH? Or just before? Depletion, right? Nothing. I is also 0, right? This is VTH. Okay. Now, what if I keep increasing the gate, so this is larger than VTH? Thank you. You have a lot of electron, right? And it becomes the inversion. Then the I is larger than 0, right? So you will see that if you do a measurement, now this will go up, right? You don't know what's the shape of the curve. We can derive it. But at least you know that it will go up, right? So this is how we get the so-called IDVG. So from here, you see that we will derive a very important concept called gate overdrive. Let me just call it VOV. It defined as VG minus VTH. So what does it mean? If I have a particular VG that I'm interested in, let's say this VG, this is the gate overdrive. Okay? How much above the VTH does the VG has? Because for a transistor, you say, I drive it really hard, right? But only those above VTH is important, right? So maybe I have transistor has a threshold voltage is 1 volt. You have a transistor which is 2 volt. We both apply 3 volts. I drive mine harder because I have 2 volts overdrive. You only have 1 volt. Then I will expect I have a much larger current. That's why this gate overdrive is an important concept. Okay, so you don't just tell people how much I apply to the gate. I also need to know what is the threshold that you can turn it on. Okay, gate overdrive. Again, here I show you this is a voltage dependence resistant, right? I change the voltage, current changes. So it is a voltage dependent resistance. So based on our understanding, right, without any equation, based on our understanding of how it works, maybe you can even tell me what happened if I change the gate oxide thickness. This one has a thin gate oxide. This is a thick gate oxide. Which one has a larger current? Thin gate oxide has a larger current, or a thick gate oxide has a larger current? Huh? Who think is thick gate oxide? Who think is thin gate oxide? Great, very good. Thin gate has larger, right? Because, say again. Excellent. Because the current depends on the capacitance, right? We did not derive any equation, but I have been telling you. The reason we have this charge is because of the capacitive coupling, right? So if I have a larger capacitance, of course, I will be able to couple more charge for the same gate voltage or same gate overdrive, right? And then you just told me that Cox is epsilon divided by T, right? So that if I have a thinner gate oxide, I have a larger capacitance, and I have a larger current. So as a result, you know that this curve belongs to thin gate oxide. This curve belongs to the thick gate oxide, right? You don't need any math, right? You know everything just from your fundamental EE class, right? Now, I also have two channel length, which called the LG. This is called LG. This one has shorter, and this one is longer. Which one has a larger current?
Be the short one.
The shorter one. Why?
Less resistance.
Yes, because after all, the transistor is just a resistor, right? So shorter one, reduce, it just means the resistance is smaller. Common sense, right? Smaller stuff, less resistance. Now, as a circuit designer, which one can you control? Do you know? Okay, someone say the length. Exactly. As a circuit controller, you can draw any transistor you want. So if you refer to this slide, This dimension is something you can control. You say, I want to make it wider, I want to make it longer or narrower. This dimension is something you cannot. Exactly, because this is process specific. Unless you are Apple, because you have a lot of order, you can say, I'm going to have so many wafers for the coming 10 years. Then maybe TSMC will modify for you, right? Otherwise, we have to take this for granted, okay? Exactly. You even build your own plant. Good. Well, very good. Okay. How about the effect of the width? Right? I have two width. Which one? Maybe you just tell me, right? For example, this one. Can you guess this is larger current? Do you think this has a smaller or larger width for a larger current?
Larger width.
Larger width. Again, common sense, just like the freeway, more lanes, right? More water flow, more car flows, right? It's just a resistor, right? Now, then how do you lay out really? Now, if we look from the top, we say that is what you can control. That is how you lay out a transistor. It's very easy. You just draw two boxes, and that's it. Okay? Because this is the bird view. It's not just bird view so simple. It is really what you do when you do the layout. So in lab 8, you are going to see something like this. You will do this type of, you won't do a layout, it generate for you. But you will see clearly you have this gate, source, and drain. That's it. Basically, it's you're just telling the machine that I have the gate in this region, and I have source and drain in this region, right? So this is W. In analog circuit, you want to have a large W because it increases your GM. GM is very important, okay? So, but you cannot make it too large. If you make it too large, you will run into a problem because my signal comes from here, right? Yeah, very good. You need to propagate all the way to here. You have the so-called gate resistance. You make it really long, yeah, looks like you have good GM, but then you have a very large RC delay. And you should also know that it's scaled as the length square. It's not just linearly. You make it double, the delay will reduce by 4 times. Okay? So there's a way we can solve this problem. What they call is called the multi-finger layout. So I think it's good to mention this. So you still do this. No. In segments, yes. So you will just reduce the length by half. Okay, you see this one is only W divided by 2. This is W. But how do I draw the rest? I will draw the, no. I will go from bottom because of the way I draw it, but it's the same, right? Bottom and top. I will do it in this way. This is the gate, okay? Now, if this is called L, this is still L. They still have the same L. But the W is divided by 2 because now I make this part the source and this 2 part the drain. And then I will connect the drain together. So you see that it's just like this. I have a freeway. All the car go from left to right, right? So in every second, I get so much amount of car. Now I reduce it by half, but however, all the car, yeah, they go from half of them go to left, half go to right at the same time. So the effective length is still W, right? It's just like water, right? The source go from left to right. You go through this W width. But here I actually reduce it to half, but I have 2 channels for you to go. One go to left, one go to right. Yes, then later I need to connect the drain together. The results will be the same. Right? So that is called multi-finger. And then what happened? Then the resistance will be reduced by half, right? And then the speed will increase by 4 times. Of course, we have overhead. We won't go into details, but you see this is the multi-finger layout. Okay, you might deal with this in the future. Okay, good. So we actually are pretty good about with the transistor already, but we need to get some math, and then derive the equation. But so let's look at this figure. I have a transistor on the left is ground, on the right is 1 volt, and then I have the gate at, for example, 5 volt, very high. This is the insulator again, right? I capacitively couple the gate to the body, and then I adjust the resistance along here, right? Because by changing the amount of the electron. So to study this, I would like to know what is the potential along this line. So here is x equal to 0. Here is x equal to L. Okay, so my goal is to find out what is the potential, right, from 0 to L. What is the potential at 0 based on this figure? 0, because it's right at the source, right? How about the potential right at the drain? Voltage of drain, right? So this is a little bit tricky. Sometimes we need to think, but we only talk about potential. There, we need to consider about the doping, the Fermi level, but we don't need to be so detailed. But the point is that we understand that the potential increase from the source to the drain. Okay, that's the main point. Whether in linear, quadratically, exponential, whatever, depends on the math, right? We don't know. But you should have the concept that it's increasing, which is common sense, right? The ball is rolling from the top of the hill to the ground, right? Of course, then this is opposite, right? Then, but so the potential keep reducing. Okay. Then I want to know what is the difference between the gate voltage and the Vx, which means Vg minus Vx. Along this channel, right? First of all, why I want to do that? Because this is the capacitance, this is the potential difference across the capacitance, right? Because this is Vx, and this is Vg. Right? So Vg minus, maybe I should just use subscript. Vg minus Vx is just the voltage across the cap. Make sense? At every point, right? Why I want to do that? Because after that, I want to derive how much electron it accumulates. That can help me to derive the current. Right? This is not difficult. Look at Vx. It's increasing, right? And Vg is constant because this is conductive. It's a metal or a polysilicon. Every point is Vg, 5 volt, right? So what is the value here? What is the value? What is Vg minus Vx when x equals to 0? 5. Very good. 5 because Vg minus is 5 minus 0. So it's 5. And what is the value at the drain? Very good. This is 4, which is equal to 5 volt minus 1 volt, right? This is 5, which is equal to 5 volt minus 0 volt, right? So this will be the change of the voltage across the capacitor, right? So I just, again, this math you cannot memorize, but you probably should have the idea now, okay, the potential difference across the capacitor is decreasing when you go to the drain. So do you have more or less electron when you go to the drain? Less, right? And even at a point, they will be the same. We'll talk about this when it is at saturation, right? But is this clear? The point is I want you to, there's no math here, right? All of you just through logical reasoning and the understanding of capacitor and how transistor work, you already can sketch this graph. And indeed, in some company, this can be an interview question, but maybe not for analog circuit, right? But when I was working in the company, some people come, okay, ask them to sketch this. If you can sketch this, you know transistor, okay? So what is the channel charge then in that case? So let's review again. What is the capacitance? Is equal to Q over V, right? Again, I told you an egg on the cup. Capacitance equal to Q over V. In this particular case, the Q, I will call it total charge. Right? And then the V is what? The potential difference across it, right? So it is Vg minus V of X. So every segment, you should obey this relationship, right? This is a capacitor. This is C. I have Q plus Q here, minus Q here, right? When I apply a voltage, which is V, right? This is just a review. Make sense? Very simple, but the point is that you need to know what is the meaning of V. V is the difference, is not one terminal. Just like Ohm's law, we keep saying that not just one terminal, it's the difference, right? So in this case, if you look at our transistor, again, we have a capacitor, Cox, which is not changing. We also have Vg, which is the same everywhere. But the bottom, we have Vx, right? So at each location, you have this relationship. Total charge equals to Cox times Vg minus Vx. Agree? Huh? It's just swapping them. But this is common sense, right? If you understand at the beginning, probably you wrote this equation already. Yeah, capacitance times the potential difference is going to be the total charge. But do you remember what are the total charge after inversion or at each state? It actually has the free electron plus the depletion charge. Correct? It's not just free electron. Look at this. I have been creating negative fixed charge before I create the mobile electron, right? So when I have mobile electron, I also have this fixed charge. This capacitor is sustaining both charge through this equation, okay? But the depletion charge is not contributing to any current flow, right? So it should not enter into my current equation, right? Luckily, I know when the depletion charge stops increasing. It is at the threshold voltage. So I basically also know that the free electron charge equals to Cox minus Vgs minus Vx minus Vth, because only those after Vth would contribute to the mobile charge. Because whatever charge you accumulate before Vgs minus Vx minus Vth equal to 0 does not contribute to the free electron. Is this okay? Basically, or you can think about Vgs minus Vth is the overdrive. So that is after the threshold voltage, we start inducing the mobile charge, right? And that's why we have this equation. Or you go back to not that good analogy, I talk about the water pipe, two sides are water, middle are ice. I keep attracting a lot of water. Unfortunately, at the beginning, they are all ice. They are not helping me to do anything, right? Only after I exert more force, somehow I attract more water instead of ice. So only those force after which I starting have the water contribute to the formation of the water, right? So that's why the free electron equation is this. I won't test this in the exam, but I want you to understand, right? With this one, then we are pretty good already, right? This is the last slide of today. We say from the last slide, I say the curve, the charge. Now I'm going to say the charge. I just call it Q, right? I just call Q e to Q free electron. I only care about this, right? Free electron equals to Cox times VGS minus VTH minus V of S, right? We went through all the reasoning, which makes sense. Some of you might even be able to guess this equation right at the beginning. The difference of the potential after the threshold voltage times Cox will be the mobile electron. This is the charge. And then we also know that the current equals to the, this is just the electron charge, right? Times the width, times the velocity, and then times the charge density. Okay? Again, this needs some time to understand, but we don't need to go over this class. Basically, but it makes sense, right? It's just like, how much water is going through this freeway? Well, I have many trucks carrying the water. What's the water flow rate? Well, it depends on how much water each truck carry. This is a Q. How much charge and electron carry? How wide is the freeway? 2-lane, 3 lanes? What is the velocity the trucks are driving, right? And Q is that, what is the density of the truck? Yeah, you're driving fast, but you only have 2 trucks every 100 meters. Your density is small. This density comes from this. So similarly, right? What is the density of the electron, which depends on the capacitor? How fast they are moving, and how wide is your transistor, and the charge they are carrying, right? What is the velocity of the electron? V equals to something called mobility times the electric field. How fast your electron can move depends on how mobile they are. Different material have different mobility. We are not talking electron in the free space. In the free space, you just use F equal to ma. You know how fast they move, right? So electric field is the force the electron feel, and then it has something called mobility. Okay, some material has high mobility, some has low mobility. For gallium arsenide has high mobility. That's why they use for RF frequency, RF application. You just trust me about this. In reality, actually, if you try to put the velocity versus the electric field, you see that it will saturate eventually. It cannot go forever, not because of relativity. It's just because if you have a very crowded place, right? I try to drag you with some force. The stronger force I drag, you will travel faster. But when I'm really fast and really strong, you cannot go increase your speed forever, because the faster you move, you actually knock on more people. You keep losing your energy. Okay, maybe too much, but I just want to say this is the slope is the mobility. Okay. We are not going to solve this equation. We solved it in E128 already. That is not our purpose. My purpose is to bring you back to the fundamental. You understand the insight, right? And the rest, you just do it yourself or check Wikipedia. Then we find that the current is mu, is W on L. Mu Cox times V GS minus VTH times VDS minus VDS squared divided by 2. Now, I can have an interview just to ask you to explain this equation. Current, of course, proportional to the width because it's a resistor. Transistor is a resistor. Inverse proportional to the length because it's a resistor. Why is related to Cox? Because it's a voltage control resistor through capacitive coupling. Larger Cox give me more electron density. What is mu? Why is related to mu? Yeah, mu is the mobility. It represents for the given electric field, how fast it will move. And why is GS minus VTH? Because after the threshold voltage, we form the electron. Otherwise, there's no mobile charge. Of course, larger GS, more coupling, so larger current. Why is VDS? Well, because it's a resistor. You apply a larger terminal voltage, you get more current, right? So if you can explain this, I think you have a good understanding, okay? So let's stop here today.